Hello. So in this video, we're gonna discuss about energy. But before we discuss about energy for chapter 7, I'm gonna first define what work is. So what is work? Work is a change in energy. Okay, so work describes, and then I haven't really defined the energy, and we'll define the energy after I define this work, but it's by doing the work, it could be either positive or negative, something changes, and that something is the energy. In chapter 6, we studied momentum and we studied impulse. Impulse describes the change in momentum. And also, how long the force is applied to change momentum is impulse. So then let's look at let's see, share the chat here. Not the chat, whiteboard. I'm going to go through the whiteboard now. Okay. Okay. Chapter 7. It's all blue, and I don't know why it's that thing. Let's see. So chapter 7 is about energy. And this is part 1, so we're going to discuss work. And in chapter 6, we define momentum. Momentum is inertia in motion, and impulse describes the change in momentum. And when the force is applied on the system, when the force is applied, force changes something. And we say how long the force acts. So it depends on how long the force acts on it, and then it changes something. And when we say this long, how long? We say how long in time. And we say force times time. When you have a how long force is applied for in time, this changes the momentum, and we say this is impulse. But how long, it may not be just time, but this long can be taken as a distance too. So how much is this external force or net force is doing acting on it to actually move the system in distance? It changes something. So distance, right? So let's say force times distance. And this is work. Change the color. This is what work is. Thickness, purple. So when you say how long in distance, when you have external force or net force applied on a system and you push it for maybe 2 meters, then you've done more work compared to you moved it on the 1 meter. If you move the system with the 5 Newton amount of work for 1 meter compared to 10 Newton amount of force and then move 1 meter, then you've done more work when you apply 10 Newton to move 1 meter. So bigger force, applied, net force, or it could be just a force. I'll define it again. Make sure to go over clearly. Bigger force is more work, right? And longer distance is also more work. You can see. But so I'm saying is that force is responsible to move the system in distance. And we describe that as a work. But let's see, how about in a case like you have a work, you have a force applied, but then the system just happens to move perpendicular to the force. Do you think the force is doing any work when the system is moving perpendicular and then the force is pushing, but it's pushing perpendicular direction? Do you think force is responsible for the movement if they're perpendicular to each other? No, right? You have to be, if the for the force to be responsible for the motion to move the system, then they have to be parallel to each other. Only the parallel component to each other do some work done by that particular force. So make sure that it's not work is not just force times distance, but also they have to be parallel to each other. So force has to be responsible for that displacement, that motion. If force applies perpendicular to the motion, no matter how much the system has moved, that force is not responsible for doing any work. So again, the work is the definition of work here. So the definition of work is equals to force times distance, how much it moved due to that work. So they need to be only the component that's parallel to each other. It could be anti-parallel, but you're looking at only along with each other. Okay, so force, and also you can see that because force is force a vector or scalar? Force is a vector. And distance or displacement, remember, if displacement is a force or vector, when you say 5 kilometers from here, you need to be specifying, is it 5 kilometers from here in the north direction, south direction? So therefore, displacement or this distance is also vector. So you have two vectors, force, that's a vector, times the distance, that's a vector. So we got to look at, we have to consider the direction, and that's why we're only picking the parts that's parallel to each other to define the work. So, and it happens that work, after that they're parallel to each other and multiplication, this turns out to be, it's just a scalar. This work doesn't have any information about directional information. work just describes how much work is done, magnitude, how much work is done for the force to move the objects in whatever the distance. So it could be positive or negative, but that's just a quantity, how much it is. It doesn't show, it has no information about direction. And remember the unit for the force is, we use Newton for the force, and then distance we use meter. So 1 Newton meter, we use a new unit that's called joule. So 1 joule is equals to 1 Newton meter. And by force is applied to move the system in whatever the distance, it changes. And this one describes, it's kind of small. This describes, I'm sorry. Change in energy. So by applying, you have some kind of a force, and then when the force actually moves the system in whatever the distance, parallel to each other, then you change the energy of that system done by that particular force. So you could be, we've learned different forces, right? You've learned gravitational force, all the other force, friction force. So these forces, because you have those force, and then that force move the system, it could be a ball, it could be something, for whatever the distance, you also change the energy due to that particular force, and you're doing some work. That force is doing some kind of a work to change its energy. All right. Let's change the color. Let's do the purple. Okay, so work is force times distance that's parallel to each other. And it's a scalar value, how much the force is done, work. And it could be positive or negative if they're anti-parallel to each other. Let's say force is applied upward, but then object has moved on downward, then it's a negative work. If the force is applied upward and then object has moved upward due to the force, and then that means that this force done a positive job. That kind of a thing. Again, I'm going to be discussing more clearly, trying to be more clear with this. But that's the definition of a work, okay? So let's look at a bowling ball example. We have a, let's say here we have a bowling ball. And this bowling ball has some kind of a weight to it, right? So there's a gravitational force applied, Fg. And then let's say you happen to have your foot immediately below. It's your feet, foot, your foot. So this is the case, study case. But then let's say the same bowling ball, but in this case, there's a different case that you have the exact same bowling ball, right? Same bowling ball. And again, you have your foot here. So it's the same bowling ball, so you're gonna have the same gravitational force. Same gravitational force, either way. But the difference with the case 1 and case 2 is that it's higher. The bowling ball is up higher, H2. Height is H2 and then H1. Let's say you just unfortunately you slip your hand and drop the bowling ball in the case 1, and then you happen to have your foot right below the bowling ball. All right, hopefully you're wearing the shoes. So either way, it's the same ball, so the force is the same, but you definitely do not wish that you don't have the bowling ball up higher and drop on your foot compared to bowling ball rather close to you, like low. It's just you just picked up and slip your hand and dropped on your foot compared to you have a bowling ball all the way up and drop it on your foot. You don't want that, right? So even though that it's same bowling ball, same weight, you get a different results because this gravitational force on the bowling ball does work. When it dropped, when the bowling ball is in a free fall, right? Then this gravitational force is doing the positive work to go down because the gravitational force and then dropping distance is pointing in the same direction. And then it hits the ground or your foot. So their gravitational force is responsible for dropping the ball and doing a positive work. But then if you have it up higher, you do more work. The gravitational force will do more work because it's the same force, but longer distance that these forces keep moving. So definitely, this case is more work done by the gravitational force. So it hurts worse. Either way, it's the same gravitational force, same force, but different distance, right? Different distance. H1 more work done by the gravitational force. We're dropping H2 distance. All right, so let's make sure to do this correctly, right? So bowling ball, gravitational force. So gravitational force is a vector, it's pointing this way. When the ball is dropped, so then, which is also a vector, that's going to be pointing downward. So this is the Fg is the force, which is the, in this case, it's a gravitational force times distance. And they're parallel to each other. So it's going to be positive Fg H1. This is going to be the amount of work done by the gravitational force. Work done by gravitational force. Let's see. This Fg times H1. Gravitational force, let me see. Gravitational force, the magnitude of gravitational force is always mass times g, constant gravitational acceleration. So here, this Fg times H1 is equals to also mg, mass of the bowling ball, times the gravitational acceleration g times H1. And that is equals to work done by the gravity on the ball. Okay. So let's see another case. Let's see. What if we have so here I have on my hand, I'm going to put a hamburger on. All right. So on my hand, I have this hamburger on. And then let's say I'm going to raise this hamburger upward. All right. And see how much work I am doing by my hand to raise this hamburger up. All right. I want to see how much work I can do to raise this hamburger upward. So I went to McDonald's website. The hamburger and a cheeseburger patties is about 33 grams. So McDonald's said, according to the McDonald's website, cheeseburger, patties, about 33 grams. And if it's a Big Mac, it's about 66 grams. So that's how much the hamburger's mass of the patty only. So let's use 50 grams. Because it's not just a patty, have a bread, buns, and a lettuce, and let's not forget the slice of cheese. Then assume the hamburger is about 50 grams. I think that's a good guess. If it's a 50 gram, then the gravitational force, let's find out the gravitational force on a hamburger. Uh-oh, where did it go? Here, sorry. Gravitational force on the hamburger is, again, mass of a hamburger times g, gravitational constant. So that's equals to Fg 50 gram times g. But we always, for the Newton, we use the kilogram. So I'm going to convert this 50 gram to a kilogram. All right. So it's going to be 0.05 kilogram times 10 meter per second square. Is everybody okay with that? So then this gravitational force on the hamburger is equals to 0.5 Newton. So let's say this hamburger on my hand have a 0.5 Newton downward. I want to find out how much work done by my hand to raise this hamburger, maybe 50 centimeter. Okay. Let's see. So I want to raise this hamburger. $50 centimeter up high by my hand. So I'm holding it. So what's that? That's a normal force. I am pushing, applying the normal force against the gravitational force on my hand. So work, to find the work done by my hand. That was going to be against the weight of hamburger. So that's also just that's equals to work to raise the hamburger, 50 centimeter by hand. So how much normal force am I applying to move the hamburger up? The normal force is equals to, I'm supporting the gravitational force, the normal force by hand. That's equals to 0.5 Newton. Same as the gravitational force of the hamburger, right? So work done by my hand is equals to the normal force times the height. That's parallel to each other. And the normal force is upward. I'm moving up high. Both of them is vertically up. So they're in the same direction. So the work done by the hand is equals to 0.5 Newton times 50 centimeter. And again, I want to make sure to convert it into a meter. And the work done by hand to raise the hamburger is 0.25 joule. So for me to raise the hamburger up high, 50 centimeter, I do work by my hand for 0.25 joule. That's how much work I do to raise a hamburger for 50 centimeter up high. This is better. 50 centimeter up high. 0.25 joule. To find the energy and in food, we use a different unit. It's still energy, calories, measurement of energy, how much gram of water, how much energy, heat energy is needed to raise that 1 gram of water for 1 degree Celsius is the definition of calorie. So then let's convert this 0.25 joule to a calorie. And this one is, how much is it? It's only 0.25 joule is only 0.6 kilocalorie. So, or sometimes in the food items, they use a big letter L, 0.6 calorie, right? This is a common way to write it. Do you know how much the Big Mac has a calorie? Big Mac, the calorie of a Big Mac is 550 calorie, or I should say 550 kilosmol calorie. So you eat a Big Mac. Okay, before you eat a Big Mac, why don't I do some exercise to use the energy that I'm going to intake? And you raise the Big Mac up for 50 centimeter up high. You're only using 0.6 calorie, which is just a, what is it, 1,000th of a calorie that you're going to intake. So it means nothing, nothing, nothing. But you know, it's not just how much you move the stuff, right? It's actually by us breathing, we use metabolism to, like, we have it breathe in and out, requires energy and all that, maintain temperature, body temperature and all that. So it's not just that, but raising hamburger up high, you think about, okay, maybe you feel guilty adding that, you know, do you want an extra cheese, slice of a cheese, and you add it and you feel guilty. Maybe you can like raise the hamburger, you know, to do some exercise to burn some calories. Like, no, you're only doing 0.6 kilocalorie, 0.25 joule. So it's not too much. All right. So that's how you can see it. I hope you understand. So, but here, what you gotta be careful that we are talking about is this is the work done by which force, right? Each time I specify this is the work done by the hand, which is the normal force, work done by the gravity, which force, right? And then how much work is done by that particular force for this motion. So either way, hamburger was raised upward. So work done by the hand at that time was 0.25 joule, and work done by, if you want to see work done by the gravity, right, which is the gravitational force, let's say, this is Ft. So how much the work is done by there's also a gravitational force applied on the hamburger when you raise the hamburger up high by your hand, and that work done by gravitational force is Fg times h. And they happen to be, Fg is pointing downward and then the height is upward. So they're anti-parallel to each other. So it becomes negative work. When the arrow, the vectors of a gravitational force vector and the displacement vector is opposite, anti-parallel to each other, the work becomes negative. Because gravitational force is doing the negative work to raise the hamburger. It's not in the same direction, it's in the opposite direction. So then, this becomes, because they're anti-parallel, negative, right? I'm going to write it in red. Negative Fg H, and that's equals to gravitational forces minus gravitational forces mg times h. So it's minus mgh. And in this case, it's minus 0.25 joule. So hand is doing the work that's positive 0.25 joule to raise it up high. And then meantime, gravitational force is doing negative work on the hamburger. All right. So let's see another example. Here, we have a box along the horizontal surface. And let's say this box was moved from this to the distance d here. This is how much the box has moved. Okay. In order to move this box, I apply a force, push force, into this direction. Okay. That's how much the force is applied to move this box. And let's analyze the work done on this system. Right. So meantime, let's say there is a friction force, and we always have a gravitational force, downward, and a normal force, upward. All right, so we have a total 4 forces applied on this box. Push force, and a normal force, gravitational force, and a friction force. Work done by, what is that? What do you think about the work done by the gravitational force? We do have some gravitational force, and then it moved for distance d. But they are perpendicular to each other. So that means that this gravitational force is applied vertically downward, and the motion is completely horizontal direction, right? Gravitational direction of the gravitational force is downward, but then displacement is horizontal. So there's no work done. There's no work done, none, by the gravitational force throughout this process. You're moving it, there's no work done by the gravitational force. How about the work done by the normal force? That's normal force times the distance, force times distance. But again, the normal force is pointing upward, but the direction displacement is horizontal. Again, they're perpendicular to each other. So again, not joule. That's why. Zero joule. No work done by the normal force. Okay. What else the force is applied on this box? Force applied on done by the friction force, let's say. Work done by the friction force is the friction force times the displacement, the distance, d. All right. And the friction force is pointing in a backward direction, but it's moved in the opposite direction. Friction force is always opposing the motion. So it's always work done by the friction force is always, because they're always opposing motion, it's always going to be negative. Friction force times distance. Green. Because they're anti-parallel. Right? And finally, there's work done by the push force. All right? And that's equals to the force applied times D. But let's look at this force, right? This force has some kind of an angle. You're pushing it with some kind of an angle. So let's decompose this. We have, use the purple. We have a force that into this direction, Fx, and then we have force that's about Fy. And this Fy, so this F force, the push force, has some kind of an angle. Since it has some kind of a vertical component, and this vertical component on the force does no work to move the box horizontally. Right? Only Fx does work. Because that's parallel to the motion. So work done by the force becomes blue equals to Fx d. Because the angle of this, angle of the force is this. And then this is the angle, direction of a displacement. So we only pick this, which is Fx. And this is d. And then the Fx is pointing in the direction along the displacement, so it's going to be positive. Okay. Then we can say, what's the work done by the total force or net work? Net force. Then we look at, we can say that's going to be the work, how many forces applied? Work done by the gravity, work done by the normal force, work done by the friction force, work done by the force applied, and that's equals to Fxd minus friction force times d. That's the total work. This is the total work done. No. Total work done on the box. And this total work done on the box, WTOT, this is going to be the same as work done by the net force. So F net it's the same thing. So if the box is moving constantly, that means net force is 0, right? If the box is moving constantly, that means acceleration is 0, let's say, moving in a straight line in a constant motion, then the net force is done. Then work done by the net force is equals 0, work done by the total force is 0. So if, but individual work done by the individual forces. So, but then you have a work of friction force, which is minus friction force times the distance, right? And then you have a work done by the F, which is only the Fx d. That means that these are not non-zero. It's not zero. They have individual forces, but what happens is Fxd is also equals to the friction force times d. And as you can imagine, push force in the horizontal direction is going to be the same as the friction force to be constant motion. You push it, right? So Fx and then a friction force. So that the net force in a parallel direction is zero. X direction is zero. Does that make sense? So when the box is moving in a constant motion, constant speed in a straight line, total work or the work done by the net force is zero. You just know that because no net force, no work done. But it doesn't mean that work done by the individual forces gonna be zero. So when you say work, you have to specify work done by the which force. Is it the work done by the net force? Is that the work done by the gravitational force? Is that a work done by the normal force? You need to make sure to specify, identify what is responsible, which agent of the force is doing what. Then that work can be positive or negative. It's just a scalar value though. And that depends on the direction of the force applied to the displacement. All right, along relative to each other. That's it. If the force is applied perpendicular to the displacement vector, then that's zero work done by that force. But then if they're pointing in the same direction, positive work. The opposite to each other, force and the displacement is opposite to each other, it's a negative. So make sure it is true. It seems simple. The work is equals to force times distance, but you need to make sure which force and which work, and then a direction of relative to force and the displacement. And it dramatically changes the results. I'm going to also define the power here too. When I mentioned that hamburger being raised 50 centimeter up high, and how much of a work did I say that I've done? It's only 0.25 joule, right? 0.25 joule, which is 0.0 kilocalorie of a work I can do by my hand. All right, and or if I'm moving in constant motion, you see. But anyway, that's 0.25 joule. But imagine, it should be something, we should classify something differently. What if like I move this hamburger up, down? Oops. What if I move this hamburger upward with spending 1 hour compared to a second? 1 hour compared to a second. It should give, okay, the work done by my hand is the same either way, but we should have something that's different to give that information. And that's the power. So let's say if I have a hamburger here, right? And then I'm moving 50 centimeter up, spending, the speed is either, let's say I spend 10 minutes raising it, or speed, how fast I'm doing it. I move it in a second. Not speed, time. In 10 minutes or in 1 second. Should have a different value. Work done Either way, work done by my hand, which is the normal force, right, is the same. But it should have a different meaning. So here we introduce power. Power is defined how much you do work per period of a time. So that's going to be joule per second equals to, there's a new unit that's called watt. Wattage. So how fast you do a work describes the power. And this is also scalar. It just shows how much you change the, how much you have a power to finish that amount of work done. And you might be familiar with the terminology that's called 1 horsepower. And that's also equals to 746 watts. Sorry about that. So 1 horsepower is 746 watts. So then let's see. The car that has the same mass, same tire, but then let's say the Porsche versus that's a hard one to say. But if you can not just only move the same distance, right, but how quickly you can move, how quickly you can move to get to that displacement, that 5 meter or 10 meter, how quickly you can do represents the power. So how quickly I can move the hamburger matters. It's not just how much work I do, but also how quickly I can do the same amount of work changes the amount of power. Okay, so that's the definition of power. And let's see, when I raise this hamburger up, well, I'm raising this hamburger upward. So that's the definition. I'm moving on. When I move this hamburger up, there is a gravitational force is doing a negative work. When I move it up, gravitational force is doing a negative work. So, but something has changed. When the gravitational force has done a negative work, something has changed. It's gaining like ability to do some kind of a work, because compared to the bowling ball that's lower and then up high, higher one, you don't want it because the gravitational force has the potential to do more positive work when it's up high compared to when it's up low. So, or like, let's think about it, archers draws the bow, right? And when I'm pulling backward, there's a spring force. I'm pulling backward against the spring force. So the spring force is doing a negative work when I'm pulling backward. But then at that position, you feel like there's some kind of a tension because now this ball gain some kind of ability to do a positive work. So when I let go, they're going to go forward, right? So it loses so it loses by moving it backward, negative work done by the elastic force, but it's gaining something. There's a change in something. Also, bowling ball moving from low to high, there's a negative work done by the gravitational force, but you know the gravitational force now, it can do positive work that's more than when it was lower. So you can see that work, I hope you see here that work is a change of energy. It's changing something. The something or the something enables to do work. All right. And so in the next video, okay, so in the next video, I'm going to discuss about energy. But I hope you understand the work and then you can apply, find the work correctly. Okay? So I'll see you in the discussion.